All right. So we are recording and ready to go on Monday, August 30th. Hey, you guys have a good weekend? Hope so. Hey, and you know what? We do have a 3-day weekend coming up because Labor Day is coming up in a few days, right? So that's something to look forward to. And so what we're doing is got this started question for you guys that some of you guys are may have solved by now. We're going to do an activity with the ruler, and then next couple days we're going to take to also solve a bunch of textbook problems, like as many as I can. A couple days from now, I want to start on projectile motion. In fact, if you want a paper ahead of time, want a head start, do you guys see the page that's clipped on the right side of your desk? Right, so that's getting that to you guys a couple days ahead of time. Okay. Not the one on the front. The one on the front is for AP, but the one on the side, on the right side, you get that one. You guys remember that a while back I gave you guys this quarter page with a couple of assignments on it. Okay. So one of those, the linear motion one, is due this coming Friday. Okay. Remember just follow that, what's going on there. Okay. And then the page that you guys just picked up pertains to the next assignment, which is due not this coming Friday, but the Friday after. All right, you guys got that? Okay. Any questions so far? All right, let's take a look at this question. We've got a ball thrown upward at 50 meters per second. I checked that, by the way, comes out to about 112 miles per hour. So let's say that you could stand on the ground and like absolutely just Nolan Ryan launch this ball straight up. How high would that ball go? What would the maximum height of that ball be? Has anybody got this solved yet? Who's got this figured out? Who solved it? Nobody yet? Okay, so I'll take you guys through it. I'll tell you what, if you can stay a step or two ahead of me, and you can get to the answer before I say what it is, then you should have pretty good confidence that you know how to solve these things. Actually, I'll take two approaches to this. All right, one approach is, let me do sort of a roundabout way that might be more intuitive. We've started tracking the speeds of this ball. Because if you throw this straight upwards at 50 meters per second, and gravity's pulling downwards, then after 1 second, how fast is it going?
40.
Yeah, 40 meters per second, right? Because it'd be losing 10 meters per second, right? That's 1 second. Okay, let's keep track. After another second, how fast? 30, then 20, then 10, then 0. Because when you hit 0 meters per second, isn't that as far up as it's going to go? See how that took 5 seconds? Right? And then it starts coming back down. Right? Because if it was 5 seconds up, isn't it going to be 5 seconds down? Right? Do you know how far anything falls in 5 seconds? Can you think of maybe an equation that could get you there? How far it falls as a function of time? How far? And it would start from rest to the top, wouldn't it? So I'm going to use the simplified form. Well, I have to go back to these three amigos. You probably be looking at the first one because the first one is the one that relates distance to time, isn't it? Right? The second one has time but no distance. The third one has distance but no time. But okay, so like this. But starting from rest, V naught would be 0. Right, so I'm going to just boil down to this right here. 1/2 g. Goodbye, green pen. Thank you for your service. GT squared. Like that, right? Okay. So sort of, again, doing like a roundabout approach, we did figure out, okay, it'd be 5 seconds up, so it must be 5 seconds down. So if I pop in 5 seconds right there, square that. I know it's picking up speed at 10 meters per second. That's called 10 meters per second squared. Okay. We got some look like that. So, hey, what's that come out to? It's about 125 meters. Oh, whoa, where have I heard that? Hey, you guys remember Paul Hewitt dropping a rock down that mine shaft? It took 5 seconds to hit the bottom. Hey, isn't this that? This is that, isn't it? About 125 meters deep. Right? But like I said, that's sort of a roundabout way to approach it. Let's do a more direct approach because we went through figuring out, well, how much time is it, all that. What if I skip straight past the time step. All right, let's go back. You could use the tax VV framework that I've been giving you, couldn't you? Right, so the tax VV checklist. Right, here's let's call it 5 variables that we're juggling around in kinematic motion. Right? What do you know from the start? What's one number that you for sure know? I mean, I gave you this one, right? And this represents what? Is that a time? What is that?
That's a velocity.
Initial velocity. Yeah. Let's call initial velocity 50 meters per second. Right? Or actually, side note here, you could approach this problem a little bit from this point of view. You could cut this problem in half and say instead of going from the bottom to the top, you go from the top to the bottom. And then you could call it final velocity 50 meters per second. You could go that way too. But we are doing it from the low point to the high point, aren't we? Okay. Remember, all these kinematic motion problems, we're always picking 2 points, right? Point A, point B, initial, final, right? Start, end, right? Because in this case, to find maximum height, this would have to be the second point, wouldn't it? And now that is the only number that I explicitly gave you. That's it. That's all you got. Or is it? What else do you guys know? I mean, you've got to know how many things.
Oh, do you know the time? It's going to be 10 seconds.
You know what? That is true. We did figure out that to go from here to here, it's 5 seconds, right? 5 seconds up, 5 down, right? And if I care about maximum height, then I care about it right at this point. So I could say 5 seconds, but how did we figure out that it was 5 seconds? We had to know what else. Yeah, something about how fast gravity's pulling, right? Because you guys remember we went 50, 40, 30, 20, 10, 0, right? That's only true on Earth. So gravity would be 10 meters per second squared, wouldn't it? Right? Or if you like 9.8, you could do 9.8, but choose that. Right? Hang on a minute. Actually, I've done something that's not exactly right. If you start applying equations exactly as I wrote that there, you're going to get something totally wrong. What's wrong with what I just wrote? How about this? Which way is this guy throwing the ball? Up. Which way is gravity pulling? Down. Uh-oh. And these are all vector quantities, right? That means that the way the guy's throwing and the way the gravity's pulling have to have what? Like opposite signs, right? Right. So see the way I wrote it, if he throws it in the positive direction and gravity is also positive direction, doesn't mean like gravity's going to like blow it away from the Earth, like anti-gravity, it's going to like rocket into space. Right? So somebody has to be negative. What do you guys feel like? Up positive or down positive? Down positive? Okay, that's what we've been doing all last week, so let's stick with that. If I do that, then isn't he throwing it in the negative direction? Right? What's most important is that these guys have opposite signs. Okay? Now that's 2 things, but you need to know 3. Yeah, you have to have 3 known quantities to be able to solve any of these. So what else do you know? There is actually one more thing.
The final velocity is going to be 0.
Exactly. Yeah, you guys hear Josh over there? He's saying the particular place we're interested in, like maximum height. Okay? If you're ever asked a maximum height question, because this is a really classic type question, then you know that at one of the points we're interested in this case the final point, there's going to be 0 velocity, right? Zero speed, 0 meters per second. Aha! Now we got 3 things, right? Okay, now, of course, you guys know what the answer to this is going to be anyway, but we're doing the more direct approach. Right. So look at those 3 known values, and keep in mind we're trying to figure out x, right? How far? Okay. Which one of those 3 formulas, the first, second, or third, is the most direct way to solve that? Okay. Well, let's see. If you try the first one, okay, we're solving for x. Okay, so we're off to a good start. Right. Well, we know all these things except for t. Right. I guess you could do it this way. You could go to that second one, and then you would know everything except for t. You could solve that and then plug it back into the first. That's actually what we did a few minutes ago when we solved this the roundabout way, right? So you totally could do that, but there's one equation that by itself it'll give it to you, and that's the third one, okay? Because look, couple velocities, acceleration, solve it for x, solve for x, right? So that's what we're going to do here. So this is this third one, by the way, is a result of a system of equations to the first 2. It's like the solution. Okay, let's see if that's actually true. So final velocity squared equals initial velocity squared plus 2ax. Okay, solve for x. Okay. Now, you guys know what the answer to this is already because we already solved it from a different point of view. It's got to be about 125 meters, right? So let's see. Check out different heat color. This goes to 0, maybe meters per second. You got to square that. Coming from now negative 50 meters per second, right? 50 upward. Now that's being squared. More about that in a moment. Okay. I know that gravity's pulling down at 10 meters per second squared, and solving for x. Okay, like that. Okay. Makes sense? All right, let's see what I get here. Got 0 is equal to 2,500 plus 20x, basically, right? With some units thrown in the mix. Okay. Now, side note here. You guys remember I made this whole deal about, well, there's got to be a negative number somewhere. In this case, we tagged it to the initial velocity, right? But what we just did, we just squared that. You guys know whenever you square something, you lose that negative information, right? Now, this will work out perfectly fine anyway, so even if I didn't make that note, then you would never know the difference. You get the exact correct answer, right? But that is a good idea to hold on in the back of your mind that this formula in particular, every once in a while, it'll run you into a little bit of trouble because sometimes you lose that negative information. Sometimes it's important. Okay. In this case, not so much, but okay. Because I'm going to just subtract this over. Call this negative 2,500 meters squared per second squared equals 20 meters per second squared x. Divide both sides by 20 meters per second squared. All right. Let's see. Well, that obviously completely cancels. All right. Seconds cancel. One of the meters cancels. We're left with 1 meter on the board. All right. And x is negative 125 meters. Right? That's right. That. All right. Now, this negative sign actually does belong there. That's actually exactly correct. Okay. I want you guys to see that checks out. That's consistent with this original setup. I remember I asked you guys, do you want to make a positive or down positive? You said, let's do down positive because that's what we did all last week. So we stuck with that. Okay. Which means you threw it in the negative direction and upwards 125 meters. That's why it's negative, because up is negative. Okay. All right, you guys good? All right. Next thing. This side. All right. Question for you guys. How can you measure your reaction time? You guys think that there's maybe a slight delay between what's going on in the outside world and your perception of it in your brain? Me speaking these words and you perceiving them. It's not all happening at the same time. There's a tiny delay, right? Except it's imperceptible, sort of by definition. I mean, you would never be able to perceive what that delay is, right? Because it's just process of your brain making sense of it. You might notice it in maybe if you're driving in a car and you see something that's like steps out in front of the road and you go to slam on the brake. There's like a tiny delay between you seeing it make sense of it, right? Or like something's flying straight at you, like you turn like, oh, there's a ball flying at me or something, right? But how can you measure that? Can you measure that with a stopwatch? That might be kind of hard because you'd be using the very tool, the very error of stopping at stopwatch is sort of what you're trying to get at, right? How can you do that? Okay. There is a way you can measure your reaction time with a ruler, and everybody has a ruler on their desk. Okay. How can you think to do that? How's this going to work? Who can figure this out? How can you use this effectively as a stopwatch? Yeah, Carson.
Don't you you take it, you drop, and see how long it takes you to grab it?
Exactly. Yeah, Carson got this figured out, and I bet a lot of you guys do too. Right, so let's suppose you team up with a friend. We're about to do this pretty soon. Okay. Your friend's holding this ruler, Right, and you are holding out your hand, and you're so you got little crab looking hand, right at the 0 centimeter mark. Okay, so here's the roller. Oop, I better turn it this way to get the 0 to the bottom. Let's say that gravity's like down. Gravity's pulling towards me, right? Okay. Right, so your friend lets go the roller, and you catch it as fast as you can. Okay? Now, yeah. Right, now, you guys see why you're going to put your fingers right at the 0 mark, right? See if you did this. What if you put your fingers like halfway up the roller, right? And then your friend drops the roller, and you catch it like the 25 centimeter mark. Was the roller actually falling for 25 centimeters? No, it was falling for like 10, right? But you lost that information, right? Or what if you hold it like this? And you catch it, it's like, man, I'm catching it right at 0. Man, I must have like hummingbird reflexes, right? But then would you be missing the falling distance of the roller to start with? Yeah, so hold your fingers right at the 0. Your friend drops it, just like surprise drop, surprise, and you catch it as fast as you can. Okay? So here's going to be our table. You're going to do trial. Let's do a few trials. Okay? Measure how far in centimeters. And that's about as much as I'll tell you. So I'll give you guys a couple of minutes. So team up with somebody. If you want to do a team of 3, that's fine. So teams of 2, teams of 3. So real fast, take a couple of minutes and measure each other's reaction times and see what you get. Right, go ahead. Okay. So you're a partner with somebody. You're taking a roller. Right. Let's say you're holding the roller and your partner's gonna catch it as fast as they can. So you surprise drop it, and then they catch it wherever they catch it. Right? And yeah, you definitely need a partner for this, right? So one person to surprise drop it, the other person to catch it as fast as they can. Unless you have passed it, possibly.
So we like dropping them.
Yeah, drop the roller and then catch it as fast as you can. Yeah, just whoever's touching
Okay, what are you
About another minute. So you guys are using centimeters and not inches, right? We're using centimeters in the class. You can convert. If you accidentally did inches, you guys know you can multiply by 2.54 and you can get the number of centimeters.
Did we need it on separate sheets of paper or just?
Oh, yeah. I'm not gonna have to turn it in.
Oh, okay.
All right, so hopefully you guys have a few drops by now. Remember in this class, we're gonna almost exclusively use the metric system. So do centimeters. If you accidentally did inches, you guys know how many centimeters are in 1 inch? Yeah, 2.54. So if you need to convert, if you're like, oh man, I did inches, oops, like 6 inches, take 6 inches, multiply by 2.54 centimeters per inch. Well, let's say you get numbers like this. Like maybe you got 25 centimeters and 17 centimeters and 26. Like that. Okay. All right. Now, what I really want to know is time. What's your reaction time? So something happens in the world, your partner dropped the ruler in this case, and you cut it as fast as you could. Isn't this effectively a measure of the time delay? But it's in centimeters. Hey, how do you think you can convert that into seconds? How could you do that? Do you think you could, hey, where's my equations? Oh, man. Ah, here it is. Do you think you could take advantage of one of these? Which one looks most applicable that's going to somehow relate distance and time for something that's in free fall? Which one? First, second, or third? First. That's the only one, right? Because the first one's the only one that has both the x and the t in it, right? So how far is the function of time? The second one doesn't tell you anything about how far the roller fell. And the third one doesn't say anything about how much time has passed, right? So it's got to be first. And the fact that you dropped the ruler from rest means you can actually simplify this. Doesn't this term go to 0? Because initial velocity would be 0 if you just drop it, right? So it just boils down to this. It's just how far is 1/2 gt squared. Well, notice I said g instead of a because it's free fall gravity. That's a type of acceleration, right? And I really want to know, what is the time, right? I'm going to do something with you that I normally say for my AP students, but let's do this. This will be fun. Let's solve this in terms of variables. Like, can you solve this before any numbers even go in? I bet you guys can. See if you can stay a step ahead of me. Can you isolate that t? Like do a few algebra steps to get t equals in terms of all these other characters? I bet you can. And cross multiply with the 2. Who's going to beat Griffin to the answer? I'm solving it. Oh, I'm going to divide the g down. 2x on g, that's t squared. Oh, I'm going to take the square root. All right, that's it right there. That's how much time is a function of how far the ruler fell. Okay. Who beat me to the answer? Yeah, all right. Got some winners out there. Right, good job, you beat me. All right, so yeah, now let's plug in these distances one by one and see what the times have been. Let me blow this up a bit. It's a little bit squeezed in there. So we got square root of 2 times the falling distance divided by Earth gravity. Right? So for example, you might get square root of 2 times 25 centimeters. Should I do this? Say 25, and then say gravity is. Did you guys feel like 9.8 or 10 today? How about 10? Let's just use sort to a round number. Okay. Of course, that's meters per second squared. Maybe I should do something like that. All right. And I get square root of 2 by 25 on 10 is 2.23 seconds. Hold on a minute. Guys, when your partner dropped the ruler, were you waiting about 2.5 seconds to catch it? That didn't sound right at all. Uh-oh. I must have done something wrong. And I did. And I did it on purpose. I'm being tricky, Griffin. What's messed up about what I did? How can I fix that? Guys, see this falling distance? If I plug in 25, that's 25 what? Centimeters, right? Not meters, right? Versus look at this unit down here for gravity. That's in meters per second squared. Because if you just do 25 and you're saying meters, here's a meter stick. Isn't it like you're just sitting there waiting for 25 of these to fall through your hand? Like, whoa, right? Isn't that what's going on? And that probably actually would take about 2.5 seconds, wouldn't it? For like 25 meters to fall through, right? I shouldn't say 25 here. I should say what? 0.25, right? Because wouldn't that be 0.25 meters? Okay. So same thing for you guys. If you cut it at the 11 centimeter mark, do 0.11 here. Right? What if you cut it at the 8 centimeter mark? 8 centimeters. Should that be 0.8? 0.08. Yeah. Good catch. 0.08. Let me see what this is. What is square root of 2 divided by 0.25 over 10? Oh yeah, that looks a lot better. 0.22 seconds. I'll try it for these other values. What is 0.17 meters? It comes out to 0.18 seconds. And what about 26 centimeters? Comes out to 0.23, or something like that. Okay. Maybe I'll take an average. What's the average of those? So 22, 18, 23, 0.21 seconds, right? And that right there is pretty much the average person's reaction time. So I was trying to pick numbers that would be approximately average. Okay. Oh, let's see, show hands. How many guys came up with a reaction time that's faster than average? Faster than 0.21 seconds? Hey, about half the class? Yep. About how averages work. All right. Okay, any questions about that? Oh, how do you find time? Right, this right here. You do 2 times the falling distance divided by Earth gravity, and that'd be all square rooted. Okay? Now, keep in mind, your falling distance, you have to convert to meters first. Like, so if it fell 25 centimeters, in terms of meters, that's 0.25 meters. Okay? So you do square root of, and then you're square rooting this entire expression. Okay? 2 times the falling distance divided by gravity. Okay? Okay. That work for everybody? Right? And yeah, you should get a reaction time that's somewhere kind of in this ballpark, about a fifth of a second, a quarter second. Okay? There is, ignoring the fact that it takes a tiny amount of time for the sound to travel from me to you. Right? That aside, there's also about a fifth of a second on top of that time delay between you hearing the words and your brain being able to process them. Yeah. All right, let's do some problems. You guys remember this page you got last week? This page? Okay. I'm gonna make up some problems from scratch on the paper in front of me that look very similar to some of these type problems. Okay. All right, so let's suppose we got here. No, let's start with a position versus time graph. You know what? I'm gonna do position versus time and velocity versus time. Okay. Maybe my questions won't be exactly what the book is asking. Maybe it'll be maybe I've got my own questions too. Okay. So let's do position in meters versus time in seconds. Velocity meters per second, time in seconds. Yep. Let's say we got 2 people in a race. 2 people in a race. Okay. And these are the paths. Ooh, I got colored pens. I need to break out these colors. Let's have pink versus teal. All right, so here's the teal person's position versus time. And here's the pink person's position versus time. Like that. Okay. Now, which of those runners is going faster? Who's going faster? The teal or the pink? Airly please. Pink, teal. Right? Who's going faster? Yeah, definitely teal, right? You guys see the velocity of teal is greater than the velocity of the pink. right? What property of the graph told you that? The slope, right? Here's B pink. Here's B teal, right? So greater slope, because the greater slope means you're acquiring more distance per an equal unit of time, right? Greater rise over run, like that. Hey, what's going on? Oh, you know, since we're talking about velocities, we may as well make these velocity graphs down here, right? Could you guys draw these two velocity graphs before I do? What does two velocity graphs look like? Did you guys get something like that? Right? You guys did that? What's going on right here? What's going on right there? Yeah, first.
They intersect.
Yeah, what's physically going on, is that maybe the two runners would be side by side. Okay, so that is the time. Well, this would be the corresponding time. Okay, so the teal runner overtakes the pink runner. Right? Guess that? Now, if you just looked at the velocity versus time graph to get that, would you ever know based on velocity versus time where one runner passes the other runner? No, you'd have no idea, right? If you were just given this graph, right? Hey, what does this gap refer to? Who can interpret that physically? Isn't this the head start that the pink runner has? Right? So pink runners head start. And that, of course, would be some number of meters. So if they were like 50 meters ahead, something like that. Right? Guess that? Because at time 0, it looks like the teal runner is at right at the start line. But the pink runner is already like way in front, right? It's got a head start. Guys good? How about this? If you look at the position, or sorry, the velocity versus time graph, okay. You guys see this little skinny rectangle right here? See the area of that rectangle? What does that represent? Isn't this how far the pink guy ran? How far pink ran? How far in meters? Right? Which would be the distance between here and here. Right? This is how far pink ran. Is that true? Okay. And I could do the same thing for the teal, couldn't I? Right? Can I take a huge rectangle? See the teal guy ran a long way, right? And that would be the difference between here and here. Right? You guys see that? Is able to navigate this a little bit? Right, any questions about these runners? All right, ready for the next thing? All right, what do we got next here? There's a question about like cows walking back to the barn. It's very similar looking graph setup. Actually, all the questions from this particular side of the page are supposed to be non-accelerated motion. So, yeah, I think if I wrote your book, I would have definitely written the chapters a little different, but that's all right. We'll go with this. Okay, so it's another position versus time graph. You got position in meters versus time in seconds. Okay. You talk about these 4 cows that are walking back home. Okay. So there's like a cow that does something like this, a cow that does something like this, cow that does something like this, and a cow that does something like this. Okay. Better label these cows. Let's call this cow A, cow B, cow C, and cow D. and make a title for this graph too. So cows walking back home. Let's call the final location home. So it'll be right here. Call that home. And we'll call position 0, like the pasture. Okay. So at time 0, looks like 3 of these cows, B, C, and D, were at the pasture, right? And maybe D's curve actually extends back like this too. That's also part of D. Okay. And hey, it looks like cow A had a head start. Cow A was already like halfway home, even when like the bell was right. Hey, cows, get home. Right? Cow A was already halfway home. You see that? Right? What's the story of cow D? I mean, it looks like here's what happened is right at time 0 the bell rings. Hey, cows, get home. A already halfway home, walks home and gets home. Notice they all get home. It just takes them different times, right? Right. Cows B and C from the pasture immediately start walking towards home, right? What is cow D doing?
He's waiting.
Yeah, he's just kind of standing around, probably munching on some grass. It takes him a while, and he realizes all his friends are going home. So after a while, he heads back, right? Okay. Who wins the race back home? I guess it turned into a cow race now.
He does.
Yeah, B, right? Cow B. And you see why? Because cow B takes the shortest time. Like gets there, farthest left on the graph, right? Gets there first before any of the other cows. Okay. Right. Then it looks like cow A gets the silver medal. He had a head start. Right, but going pretty slow, I guess. Then then it looks like cow D actually came in for the bronze, doesn't it? And cow C is feeling like that. Okay. Cow C came in last. Okay. Which cow is traveling the slowest? Who's the slowest cow? And it's not cow C. And it's not cow D.
Cow A.
Cow A. You guys see that cow A is the slowest cow? Cow A is the slowest cow. How'd you know cow A was the slowest?
Slope was wider.
Yeah, that's a real shallow slope, isn't it? Here's the slope of A. That would refer to Blossian in a position versus time curve, right? Which cow is the fastest? Actually, it's pretty close between 2 cows, isn't it?
Cow D.
Yeah, I'd probably go for cow D also. It's real close between B and D, but I didn't mean to. It looks like D is maybe slightly higher slope. Okay, so let's say cow D is the fastest because that's the greatest slope. Okay. Hey, let's rate these cows in terms of their instantaneous speeds. So it looks like D is just gonna barely beat cow B. Okay, because here's the speed of cow B. Okay. And that's going faster than cow C. Here's the cow C. Okay. And then cow A is the slowest. You see that? Okay. But you guys said cow B wins the race home. Okay. And cow C came in last. Took the most time to get there. Okay. Is that right? Right there. That's how. Okay. Send your notes. Okay. All right, next question. Here's the sun. Here's the earth. You guys know how much time it takes for sunlight to reach the earth? Anybody know?
Like 8 minutes.
Yeah, it's about 8 minutes. Hey, the time I'm going to use is like 8.3 minutes. So this is called 1 astronomical unit. And if 1 AU, 1 AU, right? If you ever hear that 1 astronomical unit, this is between the sun and the earth, right? Which does vary a little bit because Earth actually follows an elliptical path around the sun, but pretty close to circular, so doesn't change a lot. And you guys told me that the time for sunlight to reach the Earth is about 8.3 minutes. Right. So I wonder if you could figure out what is 1 astronomical unit, say in terms of like meters or kilometers, something like that. Do you think you could do that? If you also know the speed of light, c is the speed of light. It's kind of like v, right? Like velocity. It's a special number. Okay. So 3.0 times 10 to the 8. 10 to the 8. You guys know the scientific notation, right? Meters per second. 3 times 10 to the 8. Okay. One of you could solve that first. Who could tell me, say, how many meters or how many kilometers are between the sun and the earth? You guys a hint. I'm going to start. You can either do this, or you can do a dimensional analysis table, or maybe a little bit of both. How far is the Earth from the sun? Okay, who figured it out? You guys still going? All right, keep going. Got distance equals speed times time. Now, how far? You've got a speed up there, you've got a time. Might have to work with those units a little bit, but. All right, how about now? Who's got it now? All right, well, once you guys do this, I'm going to do the table version. So I'll start with the given value of 8.3 minutes, right? That takes for the sunlight to reach here. Okay. But if I want to mix it with this, and this is meters per second, you probably have to reconcile those time units, 60 seconds in a minute. Right. Now, 60 seconds per minute, should the 60 go on top or bottom? Top, yeah. Because that will allow, then you, goodbye. That true? Hey, and then there are 3 times 10 to the 8 meters per second. So I could just put that number right here, 3 times 10 to the 8 meters per second. Now the seconds go. Now I know how many meters. I'm going to do one more thing since that's a ridiculous big number of meters. More sense of kilometers, maybe? Aren't there 1,000 meters per 1 kilometer? 1,000 meters in a kilometer? Meters. So yeah, figure out how many kilometers that would be. See how this works out. So it's 8.3 by 60 by 3 by 10 to the 8, all divided by 1,000. Yep, it's that number right there. That's 150, basically, well, 149, I guess, whatever. 149 million kilometers. Okay. 149, 150 million kilometers. You guys got something like that? Okay. Let's do, let's see. How about this? Let's interpret some graphs. I'm going to put a couple of graphs side by side. I want you guys to tell me which one is possible and which one is impossible. We're going to interpret these. Now, these are both going to be position versus time. Position versus time. Okay. But the one on the left is going to be a horizontal line, and the one on the right is going to be a vertical line. Okay. What's going on this graph on the left? What is the object doing?
Moving really slowly.
Yeah, that if it's exactly horizontal, it might even be at rest. All right, so object is at rest, right? What's going on the one on the right? It's vertical. Isn't it many different positions at the same time? So would this object be moving infinitely fast? Something like that? Okay. Now, of course, that can't happen. So yeah, you can't actually have a true vertical line. So yes, this would be never going to happen. Maybe if it had a slight slope to it, it would just be moving ridiculously fast instead of infinitely fast, right? But if it's infinitely fast, it's at multiple locations at the same time, right? And that's never going to happen. Okay. All right. Any questions? Anything so far? Got about a minute left, right? Here, just to finish off today, show this on the projection. Got a question about a squirrel. A squirrel descends an 8-meter tree at a constant speed in 1.5 minutes. Then it remains at the base for about 2.5 minutes. Then walks towards an acorn on the ground for about a half minute. Then a loud noise causes the squirrel to scamper back up the tree in 0.1 minutes to the exact position on the branch where it started. Which of the following graphs accurately represents the squirrel's vertical displacement? Just look at the vertical part from the base of the tree. Right, so based on that story I just read, so the squirrel moseys on down to the ground, hangs out on the ground for a while, and then hears a loud noise and scampers back up to its starting point really fast. Which one of those graphs tells that story?
Should be A.
Yep, it's A. Remember, this is only the vertical component. So, right. So here's the squirrel at the top of the tree, makes its way down to the base, hangs out at the base for a while, and then here's a sound and it goes back to the top. Right, now this is not vertical. It has a slight slope to it, of course, but it's pretty steep. You get a squirrel out there in a hurry. And hey, look, it's at the exact same position they started at because these are position versus time graphs. Right? Guess that? All right, so tomorrow we'll do some more textbook type questions. So, all right, call that a wrap on today. Right. Who's got any questions? Any questions? All right, I will see you guys tomorrow. Have a good Monday.